So this is going to be a lecture which is going to kind of combine some of the aspects that we have learned about from Shashi on games, applied to networks, which I've been covering over the last few days. There will be a slight little bit of overlap in some of the first few slides, but I'll go through that quickly, and then we'll get to the 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 new stuff. I want to sort of preface this by saying that the field, this particular field, basically studying games on graphs or networks, is an incredibly vast field, and it's almost impossible to sort of to map out or to cover all of the various developments that have been taking place over in the last couple of decades. However, I mean, the way that I've tried to sort of frame this is sort of like a personal journey, because I've done a little bit of work on this along with Shashi, and essentially the things that I'll be talking about today are some of the papers that help contribute to the development of some of the ideas that we had. Kind of just take this as sort of, I mean, if any of you have already had some exposure to this, you may know some of it, you may not. But if this is new to you, just think of this as sort of just a kind of a preview of the complexity and the vastness of this field, and also it might give you some ideas about how ideas from statistical physics, phase transitions, and so on, like which Rajesh has talked about, can have applications over here as well. So anyhow, so hopefully this gives you an introduction to to this field, and maybe even inspire you to start working on some problems with this as well. Okay, so this is just a quote that I thought is sort of it's sort of appropriate for this particular talk. I mean, essentially, the whole sort of idea that we were trying to explore when we were looking at sort of cooperative cooperative games on some sort of topology is basically what makes an individual want to perform in a kind of an altruistic way, like and so basically I mean, just to very briefly sort of summarize, I mean, there's no way that I can kind of cover the complexity of these ideas in so briefly, but basically when you have individual agents, they could be different people, they could be animals, could be even at the level of cells. When they have to sort of when they put in a situation where they have options in front of them, and some options could involve some kind of cost, and they have to decide to what extent is this sort of beneficial for me, right? So, I mean, the best way to think about this is actually to get to some sort of real world examples. So this is just a very sort of stunning example of what we see in in our own sort of human societies. Here everybody has to kind of pitch in. I mean, so you can't have a freeloader over here. You can't have somebody who is saying, okay, fine, everybody else is going to do sort of take the load, and I don't have to do my part. But anyhow, this is more just sort of for illustrative purposes. But let's look at an example taken from the natural world. So an individual, so it might choose to act in an altruistic way, even if it requires some cost, right? In the hope that there could be some larger reward either to itself or to others in the community, right? So for example, in this V formation in birds, you see that the bird right at the front is well, I mean, maybe you do, maybe you don't. So the bird at the front actually has a slight disadvantage compared to those at the back, right? because essentially the ones at the back, they get a benefit because they can essentially travel in the wake of which is created by the flapping of the wings of the bird at the front. So the bird at the front has got like the least sort of benefit. In some sense, is taking on most of the burden, right? So why should this bird decide to say, okay, I'm going to be the one to take the load? I mean. So I mean, and of course, in reality, they sort of take turns and so on. So they have some sort of strategy which they have kind of developed. But the point is, yes. So some individuals are making a decision that they will bear a kind of a cost for the benefit of the broader, I mean, either for themselves in the long run or an immediate benefit to the community. So you can sort of view cooperation in some sense as an organizational mechanism, right? So it's something that is seen across like a wide range of scales in the natural world, and sort of altruistic behavior can form the basis of strategic collective decision making, right? So, for example, in this case over here, the ants, I mean, they all have to kind of like pitch in, right? If had they not all done this, they would not be able to sort of form a bridge like this, which would allow other ants to sort of kind of use this bridge to travel from one path to another and collect food and so on, right? So if you have one ant over here which is like saying, okay, I'm not going to do my job, the whole bridge will collapse and it'll be catastrophic for the whole community and also for the other ant as well, because they're not going to be able to get the food. So yeah, so they sort of somehow collectively managed to form like a kind of a plan for how they're going to sort of chip in. And that involves cooperation. And another, so this is possibly the most sort of extreme example of cooperation in the natural world, wherein you have this slime mold, which is under conditions of starvation. What happens is that the cells this sort of aggregate together. You can see here they sort of form like a kind of a cluster, and then they begin to sort of coalesce. And they can also form this kind of like a slug kind of morphology and sort of travel to like an optimal location. But once they find an optimal location, they sort of like set root over there, and then they start to form the sort of sprouting body, right? And what happens over here at the stalk of this body is that you have cells that basically choose to die, right? And these dead cells form the stalk, and then the cells on the top they become part of the spore. And then eventually the spore will sort of release sort of the thing for the new cells to be formed. So it'll basically sort of so but the point is that these cells over here are going to be are going to die, right? So they're going to basically make a sacrifice for the sake of the whole community. Right? So anyhow, so this is another example of collective decision making, which involves whether or not you're going to do a cooperative action for the benefit of the community, right? So all this boils down to this basic question: so why should some individual decide to cooperate in a situation where it will be more personally beneficial to act otherwise, right? To be a freeloader or to behave selfishly. So so I mean, one can imagine that if you have just like a 2% sort of case, maybe on a case by case basis, maybe the agent may say, okay, fine, in this context I will behave selfishly or not. But if that was the way that agents always behave in every context, they always behave selfishly, or they always decide to just be a freeloader, just let the other people perform some action which involves a cost, and I'll not do that. Essentially, you cannot have any sort of you can't have society, you can't have sort of any well, they cannot survive. The point is, I mean, so as you've seen in these various cases, in organisms use collective strategies to sort of adapt to situations where individually they would not have been able to do so, right? So so therefore it is important that in certain contexts that they do need to cooperate. So that's what essentially we're trying to ask. So where does this cooperation come from? So why is it so prevalent? That's the bigger question, right? So Robert Axelrod in his book, he phrased it like this. So under what conditions will cooperation emerge in a world of egos without a central authority? Okay, and so game theory, which Shashi was explaining to you. So this provides some theoretical framework for understanding the evolution of cooperation for cooperative strategies in systems of rational agents. So we've had a long discussion about what rationality is, but anyhow, so this is a framework which one can use to address this question, right? So where does cooperation sort of come from? And I mean, I don't need to go into details about what a game is, but just very quickly, it's a situation where you have two or more players. They are required to perform some action. Either could be once, like you could have a one-off game. Basically, you say I do action A or action B, and then at the end of it I get a reward. Or maybe I can do the action once and see, okay, this is going to be the outcome, and then okay, now I have another choice. Okay, now what do I do? And so you keep playing the game repeatedly, right? And yeah, so you get a payoff depending on your action. And basically, so a rational agent, as we were talking about last few days, is one that tries to maximize its own payoff and use any strategy to perform the action that they believe is going to lead to this outcome, that what's going to give me the best payoff. Incidentally, so this scene over here is from the movie. How many of you have seen this? Okay, quite a few, so I don't need to explain this. I mean, so you know the context for the scene as well, I guess, right? Okay, yeah, and okay, somehow this matrix is not showing over here, but so anyhow, but this is just a very quick sort of summary of the different kinds of some of the different types of two-player games which Shashi had covered. But this is just shown in a very kind of a compact form. So yeah, so basically, as you heard, if you have a two-player game, this is the sort of the canonical kind of payoff matrix. So you have, if you, in the case of mutual defection, both of you get a punishment. Mutual cooperation, you both get a reward. And if you cooperate while the other defects, essentially you're the sucker. So you get a sucker's payoff, while the other one has sort of a temptation to sort of defect, and vice versa, right? So that's the canonical two-player game payoff matrix. And now, depending on the values that you assign to these payoffs, you get a different game, right? So prisoner's dilemma is just defined by that hierarchy. Stag hunt, so now you basically, essentially what you've done is you swapped the R and T. So now the reward is more than the temptation. So that's the stag hunt game. Harmony, you've actually swapped the punishment and the sucker's payoff, right? So that's the snowdrift game. Sorry, did I say harmony? So I meant snowdrift. And harmony is basically, so you're now swapping T and R. So basically you have RTSP. So depending on the different sort of hierarchies that so the different hierarchy that you have for these four payoffs, you can get different games, and the different games will have different Nash equilibria and so on, which you've heard about. And also, just incidentally, these are not the only four types of games, because these are the four types of games that you get if you just start with this and you just swap. So basically, I start with TRSP and I just do some swapping. But I can have like S to be the highest payoff, as well. I can have S, then P, and So in general, you can have a vast sort of a very large number of two-player games, which I'll not get into. But that's not the point here. The reason that I wanted to mention this and show this figure is because this figure is going to kind of be important for later, especially to note the fact that suppose we set the temptation to be 1, because we have freedom to choose the values of these payoffs provided it satisfies the hierarchy, right? So if T more than R more than P more than S, I can put whatever values I want, and I can put T equals 100, R equals 50, P equals 10, and S equals 1. I can do that, right? As long as it satisfies that hierarchy. So the point is, let's just say that we set T is equal to 1. Then when R is more than 1, it's stag hunt. When R is less than 1, is prisoner's dilemma. And so on. So and similarly, when you set S to be equal to 0, when P is more than S, it's PD, and P is less than S, PD is prisoner dilemma, and P is less than S, it's the snowdrift, right? So anyway, so this will come in handy later. So that's why I thought I'll mention this here. Okay, so are agents rational? So this is again, I certainly don't want to sort of get too much into this, because this is something which, you know, it's a tough question, right? And all I can say is this. So basically, game theory, it predicts that under the conditions of the prisoner's dilemma, you should see defection, right? That's for sure. And we know that this is not something that is commonly observed in experiments and society, right? So it means that something else is at play. And so there's actually a statement from this paper over here that it's certainly not by chance that a central recurrent theme in the history of game theory is how to define rationality, right? So any working definition is sort of a negative definition, not telling us what rational agents do, but rather they do not. So there is a lot to sort of delve into over there, which is certainly not something that I'm going to get into now. But I will just mention that, you know, so the one way of thinking about this is that agents actually do not have all possible information, right? In order to make a decision of what to do, they might not. Firstly, let's just say that that we have a two-player game, and basically you say I'm doing a certain action, another player is going to do a certain action. And let's just say that we're doing it a few times. So I'm doing this and you're doing that, and then I say, okay, fine. So this is the previous decision. So based on that, I'm going to do something else. But I might not. I might make a mistake in terms of identifying what that other person has done, right? So basically, and so this actually was something that you know, is of importance when it comes to you know, like the so remember, like during the Cold War, there was sort of this thing of this there was this concept of mutually assured destruction. So it's okay, so we are not so we know that the other team, this is between the US and the Soviets, we know that the other team is going to you know, they know that if they carry out a strike, that we will also carry out a strike in retaliation, and there'll be destruction, right? So we so basically we are assuming that they are rational in the sense, and you know, they're not going to do this. But the fact, but suppose there was like an action that was taken on the other side which was misidentified. So maybe they carried out like some naval exercise, and the naval exercise was misunderstood as aggression. Then that would lead to, you know, some other behavior which is going to be quite bad. So so anyhow, so that's the point. So in reality, agents don't necessarily have all available information. How does one actually try to yes?
So anything that prevents reward maximization,
yeah,
would you call that boundary rational, or is it just lack of information?
Anything?
Lack of coping.
Well, what do you mean that prevents?
As in realistic scenarios, you might have other factors, like people might be emotional, so they might be willing to let go of some reward.
Okay, so that's the other thing that I yeah. So okay, it's sort of slightly sort of implicit in this statement over here. So it's perfectly acquired information or process all available information. So when I say process all available information, I mean process it rationally. That's what I meant to say. So basically, you take all the information and you arrive at a rational outcome. So this is assuming that you've got all the information, you do the rational thing. So you may not. You may have maybe cognitive limitations, because suppose you're taking into account too many factors, you might not be able to process all those factors and so on, right? So it's the point is, I mean, like, yeah, there are a lot of additional things that can come in the way of you making sort of a perfectly rational decision. Okay, so what I yeah, so I want to just briefly mention this, right? So we talked about like agents that are having the option to look at the previous actions and then use that information to decide what to do next, right? So this particular sort of version of the game wherein you sort of have repeated actions is what's known as the iterator's prisoner's dilemma, right? So you choose an action at each step, and then you have some sort of strategy which is going to tell you what you should do, right? So basically I play a certain action, and then the other player does that as well, and then I get some payoff. And now it's okay, fine. So I've got this payoff by playing this action. So maybe next time I should do this same action again, or do the opposite action. So I can make some sort of strategy like this, right? So and the different possibility for the kind of strategies that you can use. So the strategies, they could be deterministic. So just very simply say, okay, fine. If the previous round I lost, I'm going to switch my strategy, right? Or another strategy could be like, okay, so he played D. Okay, next round I'll play D. That's another type of strategy. Or it could be probabilistic. It could be that at every round I'm just going to flip a coin. If it goes heads, I do cooperate. If it goes tails, I defect. That could be another type of strategy. Yeah.
Maximizing the payoff or just randomly switching to
Switching strategy? Where is it?
like when you switch the strategy.
No, you don't switch the strategy. You switch the actions, right?
Sorry, your action.
Yeah. Thus, you switch the actions depending on your strategy. So that's what I was saying. So the strategy could be something like I'm just going to copy whatever the previous, whatever the other person did in the previous round. That's the strategy, right? So then I'm going to keep changing my actions based on what the strategy is. Or another strategy could be I'm just going to just keep playing something at random. That's also, I mean, so the actions keeps changing, but it's changing according to my strategy. The strategy is fixed, but the action is changing.
No, as in they are not aware of the payoff.
I mean, it's sort of implicit, right? Because it's a two-player game. Based on your actions, you get a payoff, right? So it is kind of the same thing. I mean, or it's similar, or it comes from the same place. You're looking at what the other person did, and what you did as well. Right? So basically, based on that, you say this is what happened the previous round, and now I can based on that I'm going to do something. Right? Now you might decide to ignore that information. You might say, okay, fine, this happened, but I'm going to ignore that. I'm just going to do something at random. You can do that as well. The point is that is information you have access to. Within information, you can do something, and also you can have strategies wherein you say, okay, so the last few steps, maybe the last 3 steps, this is the history, and based on this history, if this particular timeline happened, I'm going to do this. This particular timeline, I'm going to do this, and so on. So you might have a whole sort of set of possible histories, and say based on each of these histories, I'm going to do a particular action. You could do that. So all of these are strategies, and the strategy is something which is sort of unique to a given agent or specific to a given agent, but the actions can keep changing. Right. One point is that the ideal prisoner's dilemma, if it is known beforehand how many times that the game is going to be played, like let's say it's going to be played X times, right? So if it's known that it's going to be played X times, then the player can sort of by induction say that, okay, I'm just going to defect always, and the reason is because it's okay, fine. I know at the very last step, it makes sense for me to defect, right? Because I know that I can't do better than that at the very last step. So I'm going to do that at the last step. But the other player will think the same thing. So basically, what's going to happen at the last step? Both players are going to say, I'm going to defect, and so you have mutual defection. And so it's okay, fine. If at the last step he's also going to defect as well, then maybe I should defect the step before that. And then you just keep sort of working backwards, and then you realize that basically the whole timeline is just going to be defect. So if you know how many times you're going to play, then essentially it's just the same as what is the Nash equilibrium. It's just the same thing. So this only actually is going to give you something different if you don't actually know how many times, because you say, okay, fine, maybe there's still chance for me to recover. There's still a chance. So I have not done well up to now, or the previous round, but there might still be time for me to recover. Right? So if you don't know, so then that's when something can happen. Okay, so Yes.
How is it a paradox? Like,
Well, basically, it's why is it a paradox specifically? It's okay. I mean, it's because essentially, at least from what why I understand is because essentially it's like although you have in principle the option of choosing any action, essentially once you know this, you have no option. I think if the only you have only just basically one single choice or rational choice, which is to always defect. I think that's where it comes from. Although I'm not completely yes. Yeah, sure.
so empirically, this is a paradox because even so, this is the finite strategy solution. But in empirical analysis, you put people up in laboratories to play this game. Even with finite templates, they tend to go for it. Even if you tell them this is your rational strategy, even then they go for it. So that's the empirical measure of this idea.
If the number of rounds, I mean, if I do not tell the player that you have to play for this many rounds, then also defect is something that the players will always choose, right? Then
You can do that, but the okay. So that yes, okay, very good. So this actually leads me into the next sort of slide, which is about what is the best possible strategy. Right? So you could say, okay, fine, just going to always defect. That should be good for me, right? It might not be, right? So I'll tell you why. So suppose let's just say you have a population of individuals, and then you ask each individual, say, okay, fine, you guys play against each other. You guys play against each other, and so on. So basically, each pair of individuals, they go on playing against each other, and each individual has a different strategy, right? There could be any strategy. Will always defect do the best? Not necessarily. It will do fairly well, but let's just say that you have one player who is doing always cooperate. And he's playing against a large number of other players who have similar sort of positive strategy. Or another strategy could be something like, as long as I don't lose, I'm going to keep my action. If I lose, I'll switch my action. So if that player plays against someone who's always cooperating, so suppose they play C, the other player plays C. They say, okay, fine, we both done well. We see C, and so then let's just I'm just going to keep playing C. So then for the whole time, that's going to get CC. So basically, they both get R, which is more than P, right? So and so on. So basically, you have to look at what's happening at the whole level of the population. So that the D will do well against some, but on the whole, its net payoff may not be amongst all the different games may not be that high. And that's exactly what Robert Axelrod was trying to look at, to see like what could be like the best possible strategy. I mean that was the question. And so he invited people to kind of to submit some programs that encoded a strategy, and they kind of competed against each other and themselves.
Sorry to interrupt, but there's a very nice Veritasium video on the
Oh, okay.
Extremely
Cool.
well for it.
Yeah, and so basically that is that. So that he was just trying to figure out, okay, is it possible to come up with like a really good strategy that basically outperforms all of this? Now, and the strategies, yeah, so they could be like very trivial, always cooperate or always defect, and there could be a complex strategy that has some memory of actions in previous round. Now, at least in this first tournament that he organized, the winning strategy was called tit for tat. Basically, so you just mimic the opponent's actions in the next round, right? Now, that's not to say that it's necessarily the best strategy, because this strategy, the tit for tat, sort of assumes that the opponent is trying to maximize its payoff, but depending on the strategy, it may not be, because like if it's playing against a random strategy, it also will just do the same kind of. So you see here you have this agent 1, it's a random sequence, and agent 2 is just copying the previous round's action of the other agent, and it's also essentially that same sequence. So it's not going to do any better than this opponent, right? But at least on the whole, amongst all the strategies it competed against, it did well. Although later peoples have shown that there's another strategy which I just mentioned before: win, stay, lose, shift. If you win in the previous round, you just keep your action. If you lose, you just do the opposite action, and that was shown to be a little bit better. But the point is that actually there is there is no sort of universally sort of good action or good strategy which tends to dominate over all others. So that's the whole point. The point is that if you have individuals who have like a fixed strategy, and you're playing against all of them, sometimes you do well, sometimes you do badly. There are some strategies which tend to do a little bit worse than others, because random, for example, tends to do fairly badly on the whole, and some tend to slightly better than others, but there is no sort of one strategy that is like the best. But yeah, and there is still more work that is being done in this area as well. But yeah, I just want to mention that. So okay, so so all of this, yes.
Just a small addition. So there is this very cool website or game called this Evolution of Trust.
Mm-hmm.
I would request everyone to check it out after the class. It's based on this game theory population of different characters, each having their own strategy, like the copycat or the cheater.
Okay.
Or the peaceful one who's always, just doing the right thing.
Yeah.
And then you can, play around, have different iterations and see what the result is. It's very cool.
Nice.
Everyone should check it.
Sure, thanks. Okay, cool. So now that I've introduced the basic idea of having agents sort of play repeated actions, against their opponents. Let's now talk about what happens when you have interactions occurring over like a network. So up to now it was just two-player interactions, right? But in reality, so I mean the Axelrod game was different because there it was many players, but all of them are just playing one-on-one, right? But in a well mixed population, and you just have a bunch of agents just playing like one-off games against each other. So basically, if I'm playing one-on-one against this agent, one-on-one against this agent, the ones who are going to defect, obviously they are going to do well. Unless of course you introduce things like memory and so on, then of course you might have other strategies emerge. But this tends to be the case. But actually, speaking of memory, so essentially what memory is going to say is that there is you're kind of generating some sort of social network, right? Because if I don't know any of you and I start interacting with you one-on-one, those who basically I have a positive interaction with, I'm going to say, okay, fine, I'm going to maybe eventually become friends with that person, or at least remember that I have I had a positive interaction. Those who have negative interaction with, I may have something else. So essentially I'm kind of forming a network. But anyway, that's just an aside. So anyway, so the point is, so this argument which doesn't necessarily hold for interactions over networks, and so the idea is that cooperation can emerge through network reciprocity, which is basically the idea is that the cooperators can survive by forming some sort of clusters on the network, and I'll be showing you some examples of this in the following slides. So that's basically the idea. So up to now we're just looking at two players, right? So how do agents interact so update their actions if they're playing with other people on a network, other agents on a network? So let's just say that an agent is going to so agent has a bunch of neighbors. So this agent 0 has got 4 neighbors, and they're going to perform some action. So this agent is going to perform C, and we're making the assumption that these are not they are not individually playing with each of the 4 neighbors, because if you do that, then essentially that is sort of bringing it back to essentially 2-player games. We're saying that an agent is going to play an action, and this action is going to be observed by all the neighbors. So agent 0 plays a C, is going to be observed by all its neighbors, and all the other agents are going to do the same thing. So they're going to perform this action. Based on that, they're going to get some payoff, as shown by these dollars over here. So they get payoff for here, and so on. And sorry. This is I'm sorry. This is the payoff that they get from the interaction with 4, from the interaction with 1, from the interaction with 2, and so on. And they look at the total they get. So basically, suppose this the person is going to get an R. From here is going to get a S. So basically, you're going to get R plus 3S. So that's the payoff, right? And so then they say, okay, this is what my net payoff is after this particular round, and say, okay, now I'm going to update my action based on some strategy. So say that I need to change or keep my same action based on my strategy, and that strategy, it could be something that is deterministic, or it could be probabilistic, and we will be talking about this in the following slides. So the simplest thing you can do, like what is the simplest possible strategy that you can have? You can say that, all right, so I have got some total payoff, and I know what is the total payoff for my neighbors as well. So let's assume that by virtue of having this sort of network structure, you have information about the actions of your opponents, of your neighbors, and you also have information as to what is their net payoff. So in a two-player game, you know what is the payoff that they got from interacting with you, but now you also know what is the payoff they got from interacting with their neighbors. You don't know who their neighbors are, but you know, okay, they got in total, they got this much payoff, and you say, okay, fine, this neighbor has done like a D, let's say, and he's got this payoff, whereas I've done a C and I have got this payoff. So what should I do, right? So one thing that one option is basically to just look around at your neighborhood and say, okay, so this particular neighbor has done better than me, and is actually the best of the entire neighborhood. So maybe I should just copy the action of that neighbor. So this was something that was sort of looked at in the early 90s. And so this was looked at in a very simple sort of setting. So basically, you have a square lattice like this, and each site is just playing the game with all of their neighbors. Now, it doesn't matter whether it's 4 neighbors or 8 neighbors, and it also doesn't matter whether or not you interact with, you include yourself as well in the interaction. So you can also you can count yourself amongst the total payoff, and it doesn't make a difference. I mean, it makes a difference quantitatively, but not qualitatively. Let's put it like that. So the interesting, they find that you can actually get something interesting when the agents are going to update their action based on this concept which I just mentioned, which is unconditional imitation. Who is the neighbor that does the best? See what their payoff is, and see, okay, this is their action. Just copy that action. Okay. So so here what I've done is I've just have a defector in like a sea of cooperators. So basically, everyone around here is cooperating. So just ignore this for the second. So just take my word for it that you have a whole bunch of cooperators over here and a defector in the middle, right? So naively, you would think, I mean, if your only information that you had was knowing the Nash equilibrium, you say, okay, fine. What should happen is basically you start with a defector in the middle, and then everyone starts to defect, right? So it just spreads, and then eventually the whole lattice is just full of defectors. So can anyone guess? I mean, maybe if it's a bad question because some of you might know. Yes.
No, so unconditional imitation. The previous slide.
Yeah.
So you were saying something like the central player actually copies the action of the best.
It copies the action of the best unconditionally. Yeah. So there's no other. So
I think usually the other way of seeing it is that that site is occupied by the best performing neighbor. I mean, so basically
yeah.
So from a parallel point of view, that's a language which is.
So it takes over basically. You can say. Yeah. True. That's another way of thinking about it.
The progeny of the best performing guy.
Yeah.
Takes over the.
Yeah.
territory.
Right. No. Correct. So basically, yeah. Yeah. Okay. So what happens here? So basically, I've put this site at the center, and then I'm just going to let the system evolve over time. So here, by the way, I have set. I should mention this. So I've set t equals 1.9. Okay, and I've set r equals 1. Right. So basically, remember going all the way back to this slide over here. so have t equals 1. So without loss of generality, you can set r equals 1 and p equals 0, right? So when t is equal to r, I'm actually at the boundary between Price's dilemma and stagnant. So but I've set t equals 1.9, so I'm high up over there. And the p and s don't matter so much. I mean, I've set p equals 0, and actually over here I've also said s equals 0, because I mean that's what was done in this paper, but it doesn't matter too much. So yeah, so that's what it is, right? So and now this is what happens. And you will find that, and so basically, so what these 4 colors represent is that from the previous time step I was one action, next time step I'm this action, right? And so blue, red, yellow, and green, basically going from C to C, D to D, and so on. And you'll find that if for certain values of this parameter t, it'll just keep doing this forever, right? So in other words, you will find that there are these sort of clusters of cooperators that just persist in the system. They just never die. They keep moving around. So now at one point, let's wait for a cluster to emerge. Okay, so you see, yeah, here these clusters they're moving. So basically, so at one point these sites are cooperators, and at one point another sites are cooperators. But the fact is, if you just look at the average fraction of cooperators, you'll find that okay, yeah, I'll just show this picture for a second. You'll find that actually it sort of after some initial sort of variability, which is sort of initial condition dependent, you'll find that eventually it sort of just fluctuates around some fixed value, and this particular sort of outcome is independent of the initial fraction of cooperators or the starting configuration. And so the starting configuration is what I just showed over here. So here, rather than just start with one defector at the center, I've started with 10% defectors, randomly sort of chosen along over the entire lattice, and at different values of temptation, right? And you see, and all of them above 1. You see that in all these cases, you find that that you have a substantial fraction of cooperators. It starts to sort of reduce as you approach t equals 2, but even at t equals 2, you still see these sort of clusters that still sort of remain. Yeah, but of course, you see over here, if you notice one thing, there's no yellow or green. So actually what that means is that this is sort of a static pattern. So the D is staying D and the blue is staying blue. So this is actually is fascinating, because here it shows that, you know, this is actually, you have these some stable clusters of C have just sort of remained, and they're just not staying put in some sense. Yeah, and so this was very interesting. And so you know, it doesn't matter, as I said, the number of neighbors, whether it's 4, 6, and so on, or whether it includes self interactions. If you have this particular sort of strategy, where basically you just look at your best performing neighbor and just copy that action, you can actually get clusters that remain. Yeah. This one? Yeah.
Is that the time or the temptation?
Temptation. Sorry. Temptation.
So it's not time evolution.
No. It's not time evolution. No.
So you start with different initial conditions and you arrive at this particular.
Yeah. So actually, yes. So these first 5 of them are still dynamic patterns, because you see that you still have this yellow and green, right? So I just stopped it at some point in time. So you see that here you have this green sort of little squares that are sort of like essentially blinking. You see they have green squares and yellow squares. Essentially they're sort of just sort of blinking. Whereas here you have these sort of like bands that are changing.
So are there equal? Like even if you have them switching, are the green equal to the yellow?
No, is the green equal to the yellow? No, they may be equal, incidentally equal to the yellow, but the average it might be the same. I mean, because
Like a limit.
I mean, essentially, this is a steady state. That's the point. The point is that even if I run this for 10 times or 100 times longer, it will get something similar. Right? These aren't going to move around. Here it will, because this I just showed you. In this case, you have these clusters that are sort of moving, and but the average fraction of cooperators is going to be more or less the same. Although the clusters they don't stay put. And here also these clusters are mostly fairly stable. There's just some sort of fluctuation at the boundary, but that's what it can look like. Okay, so yeah, and so this is just for a regular square lattice. So this is what's very interesting. So your neighborhood is exactly the same as the neighborhood of any other neighbor, but despite that, and so you still have the cooperation which is sort of persisting in this system indefinitely, right?
What is the number of initial Ds matter?
So I mean, so this is we start with 1D, right? So
increase the number of initial.
yeah. So beyond a certain fraction of D, yes, it might not be able to sustain. Actually, I'll come to that in a few slides. Wait a minute, is it the very next slide? Oh, it is the very next slide. Yes, it is. So so this sort of answers your question. So but not exactly, but I'll get to that in a second. So basically, what these people looked at over here is when you so now we know that you can have cooperation sort of emerge sort of persisting in the lattice for some time if you have this sort of imitate the best rule, and so by changing this initial fraction of cooperators, so over here it was almost everyone's cooperation. Over here it was 90% of cooperation. But suppose I don't have such a high fraction of cooperators. Suppose I have a much lower fraction of cooperators. Well, not much, but a low fraction. The question is, how will that affect the kinds of clusters that you see? And so over here, the black correspond to defection, and the gray correspond to cooperation. Of course, just one important note over here. So here the rules are slightly different in that you only look at 4 neighbors, but apart from that, it's similar. And so what they looking at is what are the size of the different clusters that form. The cluster basically just means that there's sort of a path from any site to another site in that cluster, right? So here's one cluster. It's hard to see it, but I mean, you just have to take the word for that. Here's one cluster. Here's another cluster for this particular fraction, and then for 0.72, you see that it has some sort of larger kind of clusters that emerge. So this is the first cluster. This is the second largest cluster. Just going slightly higher to around 0.6, you see now the largest cluster that emerges. So it spans almost the entire sort of domain, right? So it's a huge cluster that suddenly emerges. Oh yeah, and another important point is that in contrast to what we were looking at in the previous slides, where everyone is just basically just updating their actions at the same time, here the actions are asynchronous. Now, as I'll mention, I'll come back to towards the end of this talk. Actually, that's also pretty important, whether it's synchronous or asynchronous. So in some sense, it's still showing the similar properties of the previous case, in that you can get cooperation persisting, but the nature of some of the dynamics that observe is going to be a little bit different. So here you no longer get the kind of geometric patterns that you were seeing in the previous case. I mean, you can see very clearly the gray, red, and blue are all cooperators. The red just means it's the largest cluster that exists. A cluster basically means that you can go from any site to any other site by some path. So there exists a path from there, and blue as well. You can go from anywhere to anywhere by one path.
Red and blue, like red.
The red is the I think the largest and the second largest. Yeah. Yes, it's a lattice.
Path means which share a common vertex.
Common word, yeah. And this was only 4 neighbors, at least for this particular study, right? So okay, yeah.
Okay, so could you explain how the game was working? Like not in this.
Yeah.
So one player plays the step, the other plays the action. Like all the other neighbors simultaneously play an action.
So basically, it's like this. So in contrast to this asynchronous sort of behavior, update rule. In the previous case, you just have rounds. You say round 1, round 2, round 3. Okay, and at a given round, everybody just says this is my action, right?
Okay.
And so based on that action, they look at their neighbor and say, okay, fine, so this is now my total payoff. And everyone sees, everyone gets a total payoff. They see the total payoff of their neighbors and say, okay, fine, round 2, okay, fine, now what do I do? And then based on the strategy, they give a new action.
Like for example, like in round 1, let's say I cooperated and like 4 of my neighbors, let's say like 1 cooperation.
Yeah.
So, okay, so like each of them gets the sum of
Each of them gets, suppose, so each of them gets the total payoff
of their
from their neighbors. So suppose I am a C and I have D, C, then I get R plus 3 S. Right? So but my neighbor who is playing a D, he might have like 1 C, but then he might have 2 other Ds or 3 other Ds. So he'll get a different payoff. And so.
Sir, like actually this thing is like done in some software and model like this.
I mean, one can simulate this, but one doesn't need any special package for this.
Or like can we generate data out of this? Like we can predict like at the value of f, this particular value like this will happen, kind of.
I mean, this is stochastic, but yes, you can find on average what will be. In fact, that's exactly what they have done over here in this slide over here. So basically, what they've done is they over a large number of trials, they've taken different system sizes, right? So basically, if it's L cross L, then it's L equals 100, 200, and so on. So up to this is a very, very large sort of system size, and they're just looking at the at a few quantities. So the quantities could be like the normalized size of the largest cluster, susceptibility, which is something that that Rajesh talked about, and also something known as Binder's fourth order cumulant, which is got this definition. But essentially, what this allows them to do, without getting into much detail, it helps them to sort of identify where the critical point is, right? So what do we mean by that? So it turns out that as you increase the system size, you see that the change in the size of the largest cluster becomes more sharp, right? So you see that here the largest cluster, it sort of kind of increases gradually as you increase f, right? But especially as you noticed over here, you see going from 0.72 to 0.76, this is sudden jump in the size of the largest cluster, and that's seen over here, right? So you see that here the largest cluster is about so big, and suddenly it becomes huge, right? So you can actually say that there exists some, if you have an infinitely large lattice, you would have like a sudden jump at some critical value. Now what that critical value is, you can actually identify that through the help of this fourth order cumulant, because you can see that as you plot this for the different system sizes, you see that they all seem to sort of intersect at some value. So anyhow, but that's not super relevant for our purposes. But the point is, one can actually do this sort of analysis and use these sort of tools from the theory of phase transitions and so on to try to study these things. And you can actually even once you find these sort of critical exponents and all these sorts of things, you can check what is if it belongs to some sort of universality class. So for example, they have found in this paper that it belongs to the same class as site percolation, and for other values of B, it belongs to other classes. But again, so this is not super relevant, but this is just to demonstrate to you that the theory of phase transitions actually has also a strong applications to these sorts of systems, which is quite unexpected if you think about it, right? Okay, so I haven't had too much time, but it's fine. I mean, I'll just mention some more things. So up to now, we've been talking about a deterministic strategy, but you can also have a probabilistic strategy, wherein each agent on a network is going to compare its payoff. So remember, it gets a payoff, it compares its payoff, let's say pi I, to that of just some randomly chosen neighbor. I have 4 neighbors, I just choose one of them at random, and its payoff is pi j, that's its total payoff. Now it could be that my payoff is more than that of the neighbor. That's okay, fine. If my payoff is more, I'll just keep my action. But if not, if the other agent's payoff is more, then it will, with some probability which is proportional to like the difference between the payoff, how much higher is this agent's payoff than mine, and you with that probability, well, of course, scale by, I mean, so we're just normalizing it here by the maximum of the degrees, and also the temptation as well. With that probability, you're going to adopt this the action of that agent, right? So essentially you're just you're not looking at information from your entire neighborhood. You're just picking one at random, just doing some sampling. You can say, I'm sampling my neighborhood. Say, okay, when pick this neighbor, okay, this payoff is more than mine. Okay, then how much more? Okay, based on that, I'm going to decide with what probability I'm going to pick the action of that neighbor. Now, it actually turns out that even with a rule like this, when you perform these rules on networks, right? So here, so remember, I spoken about ER networks and also scale-free networks. So both of these I've spoken about, right? So when you have agents that are playing this game on a network which is using this rule, you can actually find that there are three sort of regimes emerge depending on the value of, and see here this b, their parameter b is basically just the temptation. They've just assigned it a value of b. So based on, so and remember, b equals 1 is sort of the boundary. So below that is no longer presents a dilemma, because we're also assuming that r equals 1. So just above b equals 1, you see that here is going to a state of pure cooperation. So everyone is just going to cooperate. This is actually quite remarkable, right? The entire lattice, it's just filled with cooperators. And then for a slightly higher value of b, you find that essentially it's sort of fluctuating. So sometimes I'm playing c, sometimes I'm playing d, and so on. And then for even higher d, you find that there are still a few of them who are fluctuating, but most of them are just defecting, right?
So what is B?
B is just the temptation. They just called it B.
Temptation.
It's just the temptation. Yeah. The y-axis is okay. So there are two things which are plotted. One is this sort of curve over here, which is basically the average fraction of cooperators. So over here, it's basically everyone is cooperating. So this curve has gone up there, and then here you're having 80%, 60%, 40%, and so on. And here almost no one is cooperating. And the colors basically just giving the partition, like in terms of like the fraction of those who are performing a given action. So here basically everyone is cooperating. In this region over here, there are a few nodes who are just sticking to cooperation, but the rest of the nodes are just fluctuating. They're changing their action. Sometimes cooperating, sometimes defecting. And over here, there are some nodes who are fluctuating, but most of them are defecting. Right?
But in the graph, didn't we see like a like in the diagram that
Yeah.
pure cooperators and pure defectors are coexisting?
That's for a different type of network and a different type of rule.
Different type of.
So that was on a lattice, but the rule is also different as well.
The rule.
The rule, see there the rule was this one, unconditional imitation. So this is here I'm just looking at my entire neighborhood, finding the neighborhood does the best and copying it, right? Whereas here the rule is totally different. Here the rule is like I'm going to just sample the neighborhood at random, see what the total payoff is, and then based on that I'm going to make a decision. Right?
What is Ki and Kj?
Oh, K and Kj are just the degree, just the total number of links that I have. So what they find is that you can get this on ER networks as well as on scale-free networks, and in fact on scale-free networks you find that this region where you have everyone cooperates is actually even larger, right? So you can even go almost up to b equals 2, and you still find that basically most of the network is filled with cooperators. Right? And they actually they in this paper they were talking a little bit about how this might be coming about, and what they essentially pointed to was that because in this case, in these sort of networks, the topology is not is different for different, or the local topology is different for different nodes. In a lattice, everyone has the same neighborhood structure. Not so on a network. You could have a node which has 10 neighbors. Could have a node which has 1 neighbor, and so on. So obviously you're going to have some nodes whose net payoff is going to be higher, right? So that's going to give a natural kind of advantage to some nodes, right? So the nodes who have more neighbors are going to get a higher net payoff, and they're going to kind of want to cooperate for longer, unless the T becomes too large. T becomes too large, then basically it's it's not, it's the staying a cooperator is no longer beneficial. So then they'll switch. But until that point, they're going to just hang around and cooperate. And because they are cooperating, their neighbors also might want to cooperate, because okay, fine, I have a stable friend who is always cooperating. I'm going to always get some reward from this neighbor. Maybe I'll also be a cooperator. And so then that's essentially what they talked about in this paper. How essentially you have these what they call cooperator cores. So these cores are basically just staying cooperators all the time. And so and the size of this cluster will sort of change depending on your temptation. The fluctuation just red means for all time I'm cooperating. Blue means all time I'm defecting. Green means sometimes cooperating, sometimes defecting. So yeah, I will. Okay, I'm almost done. Just a few more slides. So basically, I'll just mention one more type of rule. So we just talked about a probabilistic rule, but you can actually change the extent of stochasticity in your rule, right? So basically, you can say that depending on the payoffs of my neighbors, I might want to just deterministically do something, either copy the rule or not copy the rule, or I might want to just be completely random and just just try something. Maybe at every step I flip a coin and see, do I cooperate or do I defect? And so this can actually be sort of modeled through what's called the Fermi rule, and so that's sort of explained in this paper. So the probability in this case is that is this. So basically, it's coming from this function. So again, I am node I pick a random neighbor j, right? And I look at the payoffs, and now I'm plugging the difference into this function over here. So you have some parameter beta. With the beta, you can think of it as the inverse of some temperature k or noise, right? So how does this work? So let's imagine that we're looking at the case when beta is extremely small. So when beta is extremely small, so then basically so this goes to 0, right? So then essentially it's yeah. So basically, so then k becomes very large, and so then it's sort of you don't care almost about the payoff of your neighbor j. You just do something at random, right? So that's what you get a result of this. On the other hand, when beta is very large, or in other words k is very small, it means that you are taking it entirely just depends on the difference between your payoffs, right? So basically, suppose you are doing better than your neighbor, keep your action. Suppose you're doing worse than your neighbor, you copy the action. So it's very straightforward. And by tuning this parameter beta or k, you can actually sort of go from a deterministic situation to a purely random situation, right? So this is
deterministic. Like pi is still a problem.
No, it's not, because now in this case it's like it's just an if condition. So if pi j is less than pi, I do this. If pi j is more than pi, I do this. 0 or 1. So probability 0, probability 1. Okay, so
One confusion that you're using pi for both.
sorry. I'm sorry. Yes. This maybe would have been better to call this P actually. Yeah. Right. So this pi and this pi are not the same. This pi is the payoff and this pi is the probability. So very good. Okay. Yeah. So when you apply these rules on a lattice, right? Then you find essentially that you can have two possible outcomes, right? One outcome is that all the agents are eventually just going to defect. So what we've shown over here is like the fraction of cooperators as a function of time. And you see that initially have these sort of clusters that are there, and maybe they can move around, and then they can just maybe some might die, and some might grow, and eventually it'll all just die out, right? Or you could just keep having them fluctuating forever. So these are the two options. But if you don't get a situation where everyone is going to cooperate. So that's not something that you can observe with this model, at least on a lattice. So what we actually were looking at is okay. So we know that that's what you have on a lattice, and we have. So what would happen if we start to kind of rewire the link? So remember we had talked in one of my previous lectures about the small ball network, right? So remember, a small ball network is basically, so you start off with a totally regular graph, and then you rewire some of the links at random with probability p, and for p equals 0, it's a regular graph. P equals 1, it's a totally random one, and somewhere in between is where you have these small ball properties. So we thought, let's just follow that procedure, and so we were looking at essentially how the collective behavior changes as you change p. So you see here this is basically, along this axis is the temptation, along this axis is the temperature. Now, as expected, when and also remember that when b is less than 1, it's stag hunt. Remember the matrix I showed you before, and b is more than 1 is the prisoner's dilemma. So, and the color corresponds to the fraction of cooperators. So at the, like if you just take some average, a temporal average, how many of them are going to be cooperating? If it's 1, it means everyone's cooperating. If it's 0, it means no one's cooperating. And also remember, 1 and 0 are essentially like what we call absorbing states, because once you get to that, you cannot escape that, because once everyone is cooperating, you cannot now introduce a new defector, and vice versa. So what we see is that for largest sort of temperatures, we find that you either have all defection or all cooperation in the corresponding regimes, which is not surprising. But we see two things. So first of all, we find that there exists like a small regime in the stag hunt sort of domain at large temperatures, where actually you're getting you're inducing defection, right? So you see the sort of dip over here, you're sort of inducing defection. And another thing that we start to observe is this: as you rewire, basically increasing the p, you see that there's kind of a bump that emerges, right? So essentially, all we're doing is that we're just swapping the links, and then all of a sudden you sort of find that even though b is more than 1, so it's the prisoner's dilemma, you're actually going to a stage of all cooperation. So the entire system is filled with cooperators, of course, for a certain range of temperatures. And so this essentially is like you can think of this as a sort of a topological driven transition, and this still remains an open question as to why it's coming about. So if you're asking me why, I don't know. We're still trying to figure this one out. Okay, yeah, I think this was my second last slide. So basically, just to mention, so just as we had talked in some of the previous slides, you can use a lot of the tools from looking at the theory of phase transitions that Rajesh has talked about to analyze systems like this. So for example, if you look like at the time taken to converge to the steady state. So let's say between here and here, so you have all cooperation or all defection. So as you increase the temperature, suddenly I go from all cooperation to all defection. So what happens around this transition? You find that the time taken for you to reach that state is starting to diverge close to the transition point. And in fact, you see that it sort of seems to be getting more sharp as you're increasing the system size, right? So this is sort of clearly indicative of some kind of phase transition that's happening, and so one can then use the susceptibility and all these other things to try to characterize like what could be the critical exponents and so on. So all of that is sort of talked about here in more detail. But anyway, but just to illustrate the fact that once again one can utilize these tools to study these sorts of systems as well. P. So this was just the what's it called, the probability by which you do the rewiring. Remember, so if you for the small world network, you start with a regular lattice, and then with some probability you do some rewiring, right? So 0 means it's still a lattice. 1 means it's fully rewired.
What the temperature also does? Temperature.
So yeah, temperature.
What the temperature component does to the probability?
I mean, so that's this one, right? Along this axis. So yeah, it does play a role. So as I said, so the for a range of temperatures is where you start to observe the emergence of this regime of cooperation, of pure cooperation. In the case of the Pritzker's dilemma. So when B is more than 1, it's a Pritzker's dilemma, right? So the temperature is playing a very critical role. But why specifically for this range of temperatures? It's still not clear. That is it's a hard question to answer.
Probabilities.
Oh, here, right? It's this. So k is basically 1 over beta. So basically, as I was saying, so when k goes to infinity, essentially it's purely random, and when k is 0, it's essentially deterministic. If I have a higher payoff, I stick with that. If I have a lower payoff, I just copy. So okay, so yeah, so with that, basically, I just want to mention one final thing, and I'm done. So we've talked a lot about the role of network structure on the the existence of cooperation, but does it actually? I mean, so can we conclusively answer the question? Yes, does network structure enhance cooperation? It's not clear because I mean, from looking at the literature, you seem to have there's a lot of seemingly contradictory sort of findings. Some people saying yes, it clearly does do this. Some people saying it's not doing this. But I mean, actually, these papers are not inconsistent. If you go and read all of them carefully, you'll find out maybe in some cases they've done an asynchronous update. Some cases they have considered some other specific case. So there's so much complexity that in so many different ways by which you can allow the agents to sort of utilize information from their environment. So there is I mean, it's true. I mean, in each of these cases, it's true. In some cases, you might get cooperation. In some cases, you might not. I mean, it might be responsible, but I think it's clear that there is still a lot of work to be done to have a more sort of fundamental sort of framework to try to explain this. And so there is still a lot more work to be done in this area. And so hopefully this would inspire you to do some work in this as well. I'll just finish with this, some of the references. So these are basically several of the papers that I had mentioned during the talk. And you should also check out this book, Evolution of Cooperation by Axelrod. And also some of the useful sort of video recommendations that were given as well. Those sound good. I'll check them out as well. Okay, so and with that, I'm done. So thank you. Oh, any questions? Yeah.
I mean, so with the examples you've shown here, it's a fixed strategy for the entire lattice, and then the choices are changing, right? Does it make sense to take subpopulations of different strategies, or for strategies to evolve?
So it certainly that does make sense. In fact, that is something similar to what Saptarshi is working on at the moment. Yeah. Yes.
Ideally, each agent can choose to cooperate with some neighbors and choose to defect with others.
Yes. So the assumption that's being made over here is that the links basically correspond to the like a common set of interactions that you're going to have. Basically, suppose I have a link with 4 neighbors, I'm going to do the same thing for these 4. Now you could say that I could have something like 2 types of links. Basically, one type of links for the neighbors who I'm going to maybe cooperate, another type of links for the neighbors I'm going to defect. But that raises a whole lot of other sort of complications. Not to say that it cannot be done, but I think in order to basically to come up with a kind of a more consistent theory, it was just for simplicity, it was just assume that let's just say that that each agent is going to have the same type of interaction with all of their neighbors, And also, as Shashi was mentioning, this particular approach has a very natural interpretation in some biological context. So, for example, like you could say that you're having like two types of species, and maybe one species might die out at one site and become dominated by a species of another. So maybe there could be growth of that species into a given site and so on, right? And so yeah, so one can think of a lot of different biological interpretations of this as well. So this is useful for that purpose. Yeah.
So one of the ways to beat prisoner's dilemma is if you allow the agent to communicate.
Yes.
But here you're showing something very opposite. You're saying that noise or imperfect communication or information flow is so.
Yeah.
It's very contradictory, right? There are two completely opposite ways which leads to.
Yeah, it's true, and I mean it is still not clear exactly how what exactly noise is doing, because again it should be an optimal amount of noise. If it's too much noise, again it doesn't seem to work. So somehow if there's a sufficient amount of noise, then it can lead to cooperation. Yeah, the answer to that. Huh?
How do you interpret this data in social context?
See, the problem is like coming from the interpretation of the noise as well, right? Because it's like at least in the social context, how do you interpret the noise in a social context? Now, presumably that's not something that is going to change dynamically. You could say that the different K correspond to different types of scenarios. Maybe one K could correspond to a scenario where essentially you have the information is completely noisy. You can say that, which I really have no idea what the other person is doing. And another case could be is like I have some idea, but maybe I might not give it like a sufficient weight. I may say, okay, how much do I trust this information? Maybe with some probability I will trust this information and so on. So that could be something that maybe could be what's happening with the intermediate K. But then the implications of that is going to be tricky. So say that, okay, so suppose I have some probability which I trust the information, and now that's giving me cooperation. How do you interpret that? That is not clear.